recording?
Yeah, recording now.
Alright, so we've now looked at some basics concerning Grubbs, alkene metathesis, and the mechanism. What I want to look at now is alkyne metathesis. So we've now looked at alkene metathesis. Let's look at alkyne metathesis. Now, those that have done the 3000 course, a lot of this is sort of revision. But we're going a little bit deeper, I think. This is a very interesting reaction over here. If you take this ditungsten complex, there's a threefold bond between the two tungsten atoms, right? And you react it with a alkyne, where R is typically got sterically demanding groups like tertiary butyl on the one end and H on the other. So let's just define this. So this was done by Schrock in the early 80s, and I think this is a very nice reaction. So the alkyne he used is this guy. So it's an asymmetric alkyne. And if you react this with a ditungsten complex, right, this is actually quite a stable compound. It's a tungsten tertiary butyl alkoxide. You get this guy here, where R is a tertiary butyl group. So the mechanism, okay, it's represented in this scheme with R and R, but the R on the one side was a tertiary butyl and the R on the other side was an H, right? So bear in mind, this is the alkyne. You generate this. How does this reaction proceed? Does anyone have, well, actually the mechanism is actually at the bottom there. You get basically the alkyne sees the tungsten-tungsten triple bond. It interacts with it also sort of in a 2+2 cycloaddition way like we just saw with the alkene metathesis. And it forms this cute intermediate over here, right? This ring system. This is a strain. This is in fact a metallocyclobutadiene with two metal centers, which then undergoes decomposition to form these tungsten carbine or alkylidyne complexes. Now these are Schrock type, right? The tungsten is in a +6 oxidation state. We did discuss Schrock carbines in the 2000 course very briefly, and the reason why I did that is exactly for this reason here, so you have some background. In practice, what actually happens is you form two products. So if you use this alkyne and you react it with that tungsten complex, you get two products. The one is this guy, and the other is this guy. This guy over here is unstable and it decomposes, so you can't isolate it. This guy is stable and you can isolate it, right? This is just shown in a generic fashion. Of course, if you could isolate this, you'd form two of those. Now, this guy here, this tungsten alkylidyne, is an active alkyne metathesis catalyst, it turns out. And basically, if you take that tungsten alkylidyne, that Schrock alkylidyne, and react it with another, so you can isolate that complex, right? That tungsten complex, you can isolate it in a bottle. And if you then add it to a Schlenk tube or something with another alkyne, it undergoes alkyne metathesis, as you can see here. Now, what's the mechanism? The mechanism is exactly the same as with alkene metathesis, except you have one extra 2+2 cycloaddition set. Let's look at that mechanism, just so everyone's on the same page. Let's suppose I take this isolated Schrock alkylidyne and I react it with another equivalent of this asymmetric carbine. What's going to happen? Well, what's going to happen is the following.
First, you need to decide which group you want.
Yeah, I mean, I'm just. In fact, let's for the sake of of simplicity, just say we react this with acetylene, C2H2. What's going to happen? Same thing as we have with metathesis, we get a 2 + 2 cycloaddition. And then we form this intermediate. This is a double bond. There's a tertiary butyl group sitting over there, and here's 2 H's. All right. What's going to happen now? So this is 2 + 2. We're going to have another 2 plus, well, not really a 2 + 2 cycloaddition. We're now going to just have a 2 + 2 process. And we're going to end up with this guy. So we're pushing electrons around the ring. All right, and we end up with that. Do you see what's happened there? So I get a 2 + 2, I form the metallocyclobutane butadiene ring. I get another 2 + 2 process, I form this, and then it happens again. Now this mechanism I did do in the 3000 course, but it's an important mechanism. So let's just do it again. Do you see what's happened? I end up with tertiary butyl acetylene, and I end up with, this is a plus here, and I end up with this guy here. Now, if I throw in more alkyne, it's going to keep going round and round and round. That's alkyne metathesis, right? The mechanism is the same. So,
that will then break down though, right? Because that's exactly the same thing you made last time.
well, that's a good question. That's a good question. You can't isolate it. You can't isolate it. Potentially, if you happen to try and do the alkyne metathesis with acetylene, it probably will break down because it's so unstable. But it might be that it's just stable enough that it can function as a catalyst a couple of times. In other words, it might have a couple of turnovers. It's not going to have a turnover number of 10,000, but I suspect you will have a couple of turnovers. You can't isolate it because it's too reactive, but it could work as a catalyst. You see, there's a difference if you can isolate something or if it's catalytically active. So it might work, but it's going to be pretty reactive and probably not catalyze more alkyne metathesis. But that's what I'm saying now is speculative.
Can you tune like the selectivity of it as well? Like if instead of having 2 hydrogen, we have a phenol, and we want that phenol to be on the final alkyne as well? Is there a way to tune it to make sure that the hydrogen moves to the metal complex and not the phenol?
Absolutely. You can play around with a substituent here, right? You can modulate the steric demand here on this group. In other words, here I just happen to have a tertiary butyl group. I could reduce the steric bulk there. And here I've got 3 of these O tertiary butoxyl groups. So on the metal you've got this huge steric bulk. And if I reduce the steric bulk on the carbon atom, what's going to happen? If it reacts with an alkyne, the smaller substituent is going to orientate itself this way. So yes, you can tune the selectivity. Very simply, by modulating the sterics. And you could also modulate the sterics the other way around. For example, you could decorate in principle, you can change the O-tert butoxy groups for O, something smaller or something bigger. You could put phenoxy groups there if you really want to steer the selectivity in that direction. So there are all those possibilities. Yes?
Question? Can you go to the previous slide?
To the what?
To the previous slide?
Sure.
Because there we form an intermediate. Why can't we just have a 2 + 2 cycloaddition as well? Like when we form this intermediate.
That is a,
Well, that is a representation of what I've written down here, ultimately.
Oh, okay.
So, in fact, that's a very good observation. What I've written here is the circle, right? And basically, if you look at these 2 structures here, that's precisely what it is, isn't it? I've got here two double bonds there, and here I've got 2 double bonds here. We can actually represent those 2 structures by this resonance hybrid. You can do that.
still the same.
It's just difficult, it's more difficult to then see actually how the electrons are moving to get the product, but it indeed proceeds formally via a sort of an aromatic intermediate. Yes. Yes. Let's say it like that. The circle means that there's delocalization of the electrons over the ring. Okay, so that's alkyne metathesis. That's a classic example of an alkyne metathesis catalyst. And here's the example we've just looked at. We've looked at the mechanism, very similar to alkene metathesis. Now here's a thought experiment. In fact, what I'm going to do is I'm going to, well, in fact, I'm not going to give this away. I hope you didn't look at that. What would happen? So we've looked at reacting an alkene with a carbene, Grubbs catalyst. We get alkene metathesis. We get ring opening, ring closing, polymerization, acyclic polymerization, all these variations, but ultimately the mechanism is the same. We've now looked at alkyne metathesis. If you react alkynes with Schrock-type alkylidines, we also get metathesis. What would happen if I were to react an alkyne with a catalytically active alkene? Carbene complex, like Grubbs catalyst, for example. So what I'm saying is, let's for argument's sake, say, what if I react, I'm just going to write down a generic complex. Well, let's just write N double bond Cr2 plus, and let's say this is catalytically active. But now I react it with alkyne. What do you think is going to happen?
We make like it's carbene with a long chain.
Yeah, and then that can again.
Yeah.
Let's look at it mechanistically, shall we? What's going to happen? 2 plus 2. I just have to keep my wits about me here. Not make any mistakes. Alright, that's the first step.
Ooh.
That's the first step. And what's going to happen now?
Oh, the same. Yeah, like again. Then you only
But it's like,
you get one molecule instead of two.
We're going to then get something like this, aren't we? That's the intermediate, isn't it? What's going to happen now? Now remember, we're doing this catalytically, so I've got lots of the alkyne in there, thousands of alkyne molecules. So what's going to happen next?
Another alkyne leads to the metal, and then it's going to go on.
Correct. So we're going to form something like this, aren't we? It's the same alkyne. It's going to coordinate, it's going to see that guy, and we're going to get, let's draw the mechanism out fully. Sorry. Alright, so we're going to get the alkyne here, and we're going to get a 2 plus 2 cyclo addition. So we're going to get again, so this is 2 plus 2. What we're going to get now is something like this. We're going to form something like this.
Double bond.
Just a moment. So here's an R1. Here's going to be an R1, and here's going to be an R1 as well. And now we're going to have a double bond here, and that's it. And what's going to happen now? Yes, we're going to open up the ring. So this is going to go down here, and this is going to go up here. You see what's happening? What's happening?
Polarization.
Yes, we're forming a polymer. It's just with alternating double bonds. And the process goes on and on and on. You see that?
Yeah.
So what we're in fact doing is we're polymerizing an alkyne. And so that is in fact what you can do, and this has been done. This is an example of a catalyst. This ORF is just a fluorinated substituent that's attached to the oxygen atom. RF, let's just write that down. RF is something like OCF3, 2, something like that. Okay.
If you,
Yes?
if you add it carefully though, then you just get back the same thing. You
You
get
add it-
back your reactants.
If you add carefully.
As in if it's not in excess and you don't, another alkyne does not coordinate, then
In
you
other
just
words-
get back your same reactants.
Well, that depends. That depends. I mean, yes, okay, well, I mean, these processes are in equilibrium, that's true. So the question is whether the equilibrium lies to the right or to the left. I mean, if you just add one equivalent of an alkyne, you're going to end up with this guy here.
Yeah.
Now that could potentially undergo cycloreversion and regenerate the starting materials or not, right? But you're going to get stuck here.
Yeah.
Yeah.
And it can either go back, or you can somehow, like we saw earlier, you can terminate this coupling process by adding some reagent to it, right? Which will then basically cleave off the carbene. You have reagents like that. Typically, what works very well is a ketone. So if I were to now take this guy, it's stuck, it's a complex, and add ketone to it, you would basically, this chain would fall off, right? So this would fall off and you can isolate it and you terminate the reaction. But anyway, this is basically what happens. You see, you generate a polymer, and the great thing about this polymerization is that in fact you've got alternating CC double bonds, right? And this is the catalyst that's employed. So this work was done by Schrock, and this is the mechanism. And again, you make use of this a Schrock type alkylidine in a way. Well, it is a Schrock type alkylidine. And this is another process. So in fact, there's now three things: alkene metathesis, alkyne metathesis, and alkyne polymerization with Schrock type alkylidines. Those are three processes we've learned about today. Okay, now let's look at how these things have been applied in natural product synthesis. Okay. Today, this is a catalysis course, so we need to look at the mechanism, we need to look at the catalysts and understand the catalytic mechanisms, but I also want us to look at applications. Now, Grubbs metathesis has been used widely in natural product synthesis, and I'll show some examples in a second. The first example I want to look at is this anti-cancer drug, right? Called TEI-9826. It's a prostaglandin. These are agents that are produced, I guess some of you in the class probably know more than I do about these compounds. Who's done biochemistry? Right, so what are these compounds? Prostaglandins, have you heard of them?
Our biochemistry classes.
It was
It was just cell bio.
Oh, okay.
It's in that class.
Well, these are compounds that play an important role in the body in terms of immune system. It's implicated in the functioning of the immune system. Also, if I remember correctly, people get sick. These are, in other words, if a person is ill, these are sort of synthesized by the body. So it's a class of compounds, prostaglandins, that always have a 5-membered ring system with an alkyl chain attached to it, right? And it's somehow functionalized. Actually, I know someone that did a PhD in synthesizing these, so they're important biomolecules. Now, this specific prostaglandin here, this is a synthetic one, it so happens is active against a strain of cisplatin-resistant cancer. Now, some of you might know that one of the things that I'm kind of interested in pursuing now is a bit of ruthenium anti-cancer drug research here. And cisplatin is sort of the gold standard, right? It's an anti-cancer drug or an anti-cancer agent. And when you when you test anti-cancer activity of compounds, you always do it relative to cisplatin. So this is like literally a gold standard, okay? What is cisplatin, just to remind us? Platinum, sorry. A very simple platinum 2 compound, and it's anti-cancer active. Some strains of cancer are, however, resistant to it, so you need new drugs. This has been identified as one that works particularly well against such tumors, and it needs to be synthesized, right? So we're not talking about organic synthesis. So all I want to highlight in the synthetic route, so this is a multi-step synthesis, is you can see going from 4 to 5, what have we done? Ring closing metathesis. And G2 is what? Grubbs generation 2. Okay? So look at that. You close up, you zip up the ring, and then you basically made the prostaglandin, and then in another synthetic step, well, that looks to me like some sort of an aldol condensation, kind of, isn't it? Ketone plus, so you probably react this with the base and then react it with this, and then you can attach the chain there and then hydrate it to get the 1,3 ketone alkene. You guys recognize this? This is sort of a aldol condensation, right? Something like that. Anyway, so there you can see a typical example of how this is used. You zip up the ring, and what is the other product? So if I were to actually carry out this reaction, this transformation from 4 to 5, what would I actually observe? Yes, correct. I'd see gas bubbles forming, which would be the ethylene, or would be the ethene. If you're in a laboratory and you're carrying out the reaction, right? Because these two are so close together, I think the chances of there being cross-metathesis are very limited. Very, very limited indeed. Also because, you know, this is quite a big molecule, so to have 2 of them on the ruthenium sensor is very unlikely. So you're going to probably get a very high selectivity of the ring-closed product. So that's one nice example. Here we have another example. So this is in fact a neurotopic agent, okay? Very important, so it's got biological activity. Look at that molecule, it looks very difficult to synthesize it. But one of the earlier steps in the synthesis, so this 8, 9, 10, 11, this is the steps in the synthesis. So between steps 8 and 9, what have they done?
It's also ring closed.
Sorry?
It's also ring closed.
Correct. I mean, you form quite a strained ring system. Look, well, it's not, I guess it's a 5-membered ring system. But in this case, they've used the first generation catalyst, right? But it works. So, I mean, imagine, here's a thought experiment as an organic chemist. Imagine trying to construct such a ring system, you know, using conventional organic chemistry would be very difficult, wouldn't it? So you see, the point here is that catalysis and organometallic chemistry and organic chemistry have overlapped, right? And these days, organic chemists use a lot of these new catalysts to do previously impossible synthetic transformations and make very important biomolecules. This is an antibiotic. Kendomycin, again, we employ a ring-closing metathesis strategy, as you can see here. And these are protecting groups and stuff like that, that's not so important. But check this out, this is a 30-step synthesis. Okay? And to go from 27, and without this ring closing metathesis, you wouldn't be able to construct this ring system. It would be hopeless. So this is the art of total synthesis, using catalysts that inorganic chemists make, the organic chemists can make ever more exciting and interesting molecules. And this is just to finish this whole business. This molecule here, right, believe it or not, someone has synthesized this, employs in six synthetic steps, ring closing metathesis. So, and then you can see this comes from a review that was written by Fürstner. And this molecule, incidentally, is something that's generated, it's a toxic substance that's implicated in food poisoning. And so if people, or it's something that causes food poisoning, if I understand it correctly. So it's a natural product, and scientists have managed to actually synthesize it. But you can clearly see that this is a very important field, and what we've looked at now is the applications mostly of ring closing metathesis. Don't forget, you can also do make some natural products by alkyne ring closing metathesis, or you have a similar sort of thing with if you have alkyne functionalities. And also don't forget this business of polymerizations of alkynes and stuff like that. Any questions? All right, we're now going to move on to the next topic. We're running a bit behind schedule. You will notice I have made some changes as we're going to the schedule. That schedule that I gave was sort of a wish list of things that I wanted to get through, but I think it's extremely ambitious. So, we're going to take things slowly. It doesn't help going through like 10 different catalytic processes, and nobody really knows what's going on. So we are running behind schedule, I'm aware of that, but I don't see that as a problem. The next topic is carbonylation and hydroformylation. So we've now discussed alkene and alkyne metathesis, we've discussed polymerization, stereoselective polymerization, we've looked at some, in the first lecture we discussed surface catalysis. We've looked in detail at some heterogeneous processes, Fischer-Tropsch, and so we're making progress. The next topic is carbonylation. Now, what is carbonylation? Carbonylation is simply the attachment of a carbonyl group to a molecule. We call that carbonylation. Now, in inorganic chemistry, strictly speaking, if you attach a CO group, which we discussed in detail, the Dewar-Chat Duncanson model and all that, if we attach a CO to a transition metal, strictly speaking, that is a carbonylation reaction. You also have decarbonylation reactions. But in organic chemistry, this would be an example of a classic carbonylation reaction, converting methanol to acetic acid. Basically, all you have to do is somehow incorporate a CO group onto the methanol, and you have acetic acid. Notice that this process is thermodynamically quite favorable, minus 75 kilojoules per mole. The problem is that if you take methanol and you bubble carbon monoxide through it, you ain't going to get acetic acid. You need a catalyst. So there's a very high activation energy barrier associated with this process. But anyway, that's the formal definition of a carbonylation. Now I'm going to cut to the chase, and we're going to go straight to concerning the synthesis of acetic acid from methanol. This is, of course, something that's highly desirable, right? Acetic acid is a very important starting material. You, for example, have it in vinegar, right? But it has other uses because it's got this nice functional group here which can be altered and changed. It's an important industrial starting material. Methanol is quite readily available. So to get from methanol to carbon to acetic acid is, of course, something that's very desirable. And in the 1960s, Monsanto, which is this company which I guess now has a very bad name, a bad reputation in the press because they've been accused of, genetically modifying foods and stuff like that. But this company, Monsanto, in the 1960s came up with this process, and it's called the Monsanto acetic acid process. Very important. It is a catalytic carbonylation of essentially converting methanol to acetic acid. Now let's look at this catalyst cycle step for step. All right, what's happening here? Let's start over here, 1. This is a rhodium catalyst. It's a rhodium, well, it's anionic, right? So it's rhodium I2CO2 cis minus. So what's the oxidation state of the rhodium there? Plus? No. 1. The whole thing is negatively charged. Iodine is minus, so it's plus 1. How many valence electrons does that guy have? Iridium is group 9. It's iridium 1. So how many valence electrons? 16. It's like Vasquez complex. Right. Now forget about the stuff on the right. We're going to come back to this in a moment. Just completely ignore that for a moment, please, and concentrate just on the central cycle. Remember in the second lecture we looked at all those elementary reaction steps. Now you're going to see how, in all the catalyst cycles, we study how they are relevant. If I take a 16 valence electron complex, and we saw this with Vasquez complex, and I react it with methyl iodide, what happens? Correct. Oxidative addition. And that's precisely what happens. So if you feed methyl iodide into this catalyst cycle, you get oxidative addition. Remember, trans-stereochemistry, there we see it. Same with Vasquez complex, because it follows an ionic mechanism. And we get this now rhodium plus 3, because remember oxidative addition increases the oxidation state of the metal by plus 2. We have rhodium plus 3 intermediate. Now check what happens between step 2 and step 3. Correct, migratory insertion. You see, you've got the tools. So what happens is the CO inserts into the CH3 group, and we get a rhodium acyl group. But this whole process now is sort of happening under CO pressure. So a CO then comes in, okay, and recoordinates to the rhodium sensor, so that's just a recoordination. And then what happens in this last step? Correct, reductive elimination. We eliminate the COCH3I, and we are left with that guy over there, back where we started. Very simple. Now, that's basically the cycle, and what we eliminate, check this out, is this acid iodide, right? Now that acid iodide gets fed into another cycle here. So this is now, imagine this is a big process with different modules. And essentially, if you react this guy with water, what's going to happen? This is organic chemistry.
Substitution.
Correct. You're going to replace the I with an OH, and you're going to generate hydrogen iodide, aren't you? So check out what's happening here. This guy reacts with water and forms acetic acid, the desired product, and the other product is hydrogen iodide. The hydrogen iodide reacts with methanol to form methyl iodide. Right? Do you see that? Okay. So that's the Monsanto acetic acid process, converting methanol to acetic acid. So how it actually works, right? Overall. Methanol goes in, it is converted to methyl iodide. Then that loops into this catalyst cycle. We, by oxidative addition, migratory insertion, reductive elimination, generate the acid iodide, which is then, by reaction with water, converted to acetic acid, and we regenerate the HI. So everything is sort of interlinked. Do you see that? Right, so that's the Monsanto process. It turns out that the rate determining step is the oxidative addition of methyl iodide to the rhodium center. That's basically the rate determining step according to experimental work and calculation. So that's going to slow things down. Now in the late 90s, what guys decided to do at BP, so this is not Monsanto, this is British Petroleum, is all they did was they replaced rhodium with iridium. And you have exactly the same catalyst cycle. It's just depicted slightly differently, but it's basically exactly the same. So we've got the square planar iridium complex, and you can basically make acetic acid from methanol. So basically, you see how this is another way that you can think of the cycle. Methanol in reacts with hydrogen iodide, that feeds into the cycle. You generate basically from this whole process the acid iodide, which then reacts with water to form acetic acid. So methanol in, acetic acid out, overall. Now it's exactly the same as the Monsanto process, except rhodium has been replaced with iridium. And it turns out that making that simple modification results in the oxidative addition reaction being, and this has been studied kinetically, which is the slow step in the Monsanto process, 150 times faster. In fact, it's so fast, the oxidative addition, that it's no longer, in this cycle, the rate determining step. The rate determining step is, in fact, the migratory insertion, 3 to 4. So by simply changing from rhodium to iridium, you completely change the energetics of the reaction. This is a much, much, much faster and more efficient catalyst. What is the disadvantage? Everything's faster, 150 times faster in terms of kinetics, rate determining step. What? No side reactions, mechanism is the same. Sorry? Iridium is extremely expensive. Rhodium is expensive too, but iridium, very expensive. But the fact that the process is so much faster and more efficient actually offsets the cost of the rhodium. And this is now a commercially available process. So, the next process, so we're looking now at carbonylation reactions. This is called the Tennessee-Eastman process. This is also a type of carbonylation reaction. We use, again, the same catalyst that we're using in the Monsanto acetic acid process. Basically, everything is exactly the same, except this side over here. We feed also methyl iodide into the cycle, and we eliminate the acid iodide. So this cycle is actually identical to what we see with the Cativa process and the Monsanto process. But check out what happens in the Tennessee-Eastman process. That guy reacts then with lithium, with this guy here. Now what happens if I react this acid iodide with this guy here? What's going to happen? Well, they're going to couple, and you're going to form what? What is this? What do we call this? Acetic anhydride. Very important starting material. Very, very important starting material industrially. What is it used for? I think it's used in the synthesis of aspirin, for example. Now, so actually this process is really, in a way, identical to the Monsanto process, except that we do a coupling here. Now what's happening here? Let's look at this side of the cycle. Here we start off with an ester. This is methyl methanoate. So that's the feedstock, right? The methyl methanoate reacts with lithium iodide to form this guy here and methyl iodide. So what's that transformation there? What's happening there chemically? Ester cleavage. We have an ester, and we end up with methyl. It's kind of an ester cleavage, methyl iodide, and the lithium
So it's Li plus O
methanoate.
minus.
Sorry?
It's O minus and Li plus methyl.
Yes.
Yeah.
Yes, exactly. Actually, sorry, this is not methyl methanoate, this is ethyl methanoate, right? You see, because there's 2 carbon atoms there. So that's the feedstock. Ethyl methanoate gets converted to this lithium ethanoate and methyl iodide. That goes into the cycle to generate this guy here. And you basically form acetic anhydride. So it's kind of, again, these two interlocking cycles. So this process is very similar to the two processes we saw a moment ago. And this is used to make acetic anhydride, and you use the same catalyst. So this, I think, these are very important processes. These three processes, just to revise, are industrially used carbonylation reactions converting a low quality feedstock to a high quality feedstock by introducing a CO group ultimately. And that happens by migratory insertion, right? That's the key step, and you can only do that at a metal. Now, that's the story for carbonylation. Now, there is another process called hydroformylation, right? Where carbonylation is just inserting a CO group onto a molecule. Hydroformylation is defined as essentially adding hydrogen and CO. And typically, hydroformylation in the classical sense is adding H2 and CO onto an alkene. Now, if you add H2 and CO onto an alkene, what are you going to get? Well, you're going to get an aldehyde onto you. And there you see it. Now, we have a question here of regioselectivity. This is a classic case of regioselectivity. We can either install the ketone at the end of the chain, or we can install it here, can't we? You see, the CO can either hop on there to form a so-called N, normal, linear product, or the CO can hop on here and we can hydrogenate the other carbon to form a so-called what we call iso product. So in hydroformylation of alkenes, we always distinguish between N and iso. N is just the normal linear carbonyl, right, where the CO is installed at the end, and iso is where it's installed in the second last carbon. And hydroformylation is really now about controlling the N to iso ratio of the hydroformylation process. H2 plus CO, what's that? Syngas, exactly. So you typically take an alkene, you put it in a reactor with a suitable catalyst, pressurize it with syngas, and basically you get the products off. Very beautiful process. It started in the 1930s in Germany, Ruhrchemie, Otto Rühlem, and he basically found out that you can do hydroformylation using cobalt. Now, cobalt tetracarbonyl is actually, this is the active catalyst species in the hydroformylation. The first hydroformylation catalyst is HCOCO4. Now this is basically a hydride attached to the carbonyl group that doesn't exist in a bottle. I mean, you don't have HCOCO4. What you do have is CO2CO8, but we'll look at the mechanism in a moment. This is the first example of an active hydroformylation catalyst, 1930s, and well, it's industrially important. Here's some information about it, because converting alkenes to aldehydes or ketones is of paramount importance, right? Because if you've installed a CO functional group there, you can use it for all sorts of things. They're just much higher commodities than just a straight alkene. So it's a very important process. And basically it's also used in the synthesis of these hydroformylated alkenes is used in the synthesis, for example, of detergents and soaps and stuff like that. But it's a fundamentally important process. That's why it's important. So again, 1938, also von Rühlem, Ruhrchemie, they did hydroformylation with this complex. What I want us to look at now is the mechanism of this hydroformylation, and let's do this step for step. And in fact, I'm not going to say anything, because I want you guys to tell me what's happening there. So we start off with HCOCO4, that is a carbonyl hydride. The oxidation state of that carbon, of that cobalt is what? +1. Right, now what's happening in the first step? Alkene coordination and simultaneously carbon decarbonylation. So competitive coordination, if you will. All right, what's happening in the second step? Yes. Yes. Two things are depicted there. The first is that we have a CO going on, basically, and we have alkene insertion into the hydride. So we end up with what? We end up with a cobalt alkyl group. Do you see that? Does everyone follow that, what's going on in that step? There's actually two steps in one. We can actually represent it if we want to with two steps. Alkene insertion into the hydride followed by CO attachment or carbonylation, if you will, at the cobalt center. We've represented it here in one step because it might be a concerted process. In other words, it happens sort of all together. What happens in the next step? Migratory insertion, right? And this is a classic case where another CO goes on, check it out, and induces the migratory insertion of one of the CO groups already bound to the cobalt to generate the acyl group. If you go to lecture 2, I gave an example of that where you can sort of drive a migratory insertion, remember, with a phosphine. Here what's happening is the CO says, I want to go on, but there's no space for me, so it forces one of the carbonyl groups to do a migratory insertion into this cobalt alkyl chain. And what's finally now the last step? Now this is an interesting step. What's happening in the last step to close the cycle? Sorry?
Yeah, I was gonna say oxidative division and elimination, but you keep hydrogen.
Well, a couple of stuff might be happening there. What might be happening there? Let's think about this. What we end up with is an H sitting on the cobalt. Obviously, and we eliminate, you will see that this chain that we've built up with an H at the end. I mean, I've just represented